slideshow. Oh, because I changed name. Okay, should be working. Yeah. So first thing, a very important thing, we will have a midterm next Friday. Because we have 2 midterms. So we have first midterm next Friday, and there is I sent out a event announcement, so you should all see the details. Basically, it's a closed book exam, but I will give you some of the equations. In particular, this. Wait, where is this? Yeah, weird place. Okay. Wait. Oh. Okay, I'm using wrong side. Okay. Anyway, so midterm should be on next Friday. Is this? Oh, excuse me. Let me try to fix the streaming. How do I get this smaller? Yeah. Next Friday will be midterm, and it's a closed book exam, but I'm going to give you, let's see, is it working? Yeah. Some of the equations. So in particular, these two most important equations will be given. So synthesis equation and analysis equation, although you should really get familiar with them, because we are going to see them throughout the whole every following course. The whole following course, we are going to see them in slightly different forms. Okay? Very important is the first of the Fourier transform pairs we are seeing. Okay? And I'm going to also give you a table of the Fourier properties. So the range of the course is chapter 1, chapter 2, and chapter 3 in half, and we are going to do it until the properties of the Fourier transform. So let's try to jump. Wait, let's see if I can do this. Okay, so those properties. So yeah, so this table will be given, and well, the properties basically, whenever you need to use them, you refer to this table. But it's also good to get familiar with them, and we'll cover this today or Friday. Okay, and anyway, let's back to the class. So as we said, this time we give the derivation of this Fourier series relation equations. So there is a synthesis equation and the analysis equation. And we are saying for any continuous and periodic signal, then we can write this periodic signal in terms of the sum of harmonic complex exponentials. So it's exponential e to the jk omega naught t, where omega naught is related to the fundamental period of your signal, big T. So omega naught equal to 2 pi divided by t. And you are writing your x of t as a linear combination of those e to the jk omega naught t, and with different ak. And we derive this analysis relationship, where we can calculate ak from x directly by doing this integral. So 1 t, and you integrate over one period, x of t times e to the minus jk omega naught t dt. Okay. So you can get ak from x in this equation, and you can get x from ak with this equation. So really, if you describe x of t or you describe ak, you can either describe your xt of just write down your x of t for one period, or you can just list all the ak. Both of them will tell you full information about your continuous periodic function. And yeah, and but now we see that we can try to combine different ak e to jk omega naught t into x of t. So we see those examples, and we have this really weird example of this square wave function. So we have x look at this, so it's 1 at some place, some interval, and 0 at the other interval, so it's discontinuous. And but when we plug in our formula, we find out that we can still find AK. AK is some finite value and it is decaying, and now we are thinking, does this make sense? We are approximating this discontinuous x of t with this e to the jk omega naught t, which is continuous. So how is this possible? Okay. So today we are mainly going to cover the convergence of Fourier series, and we will give out conditions to the periodic signals, such that so if the signal satisfies these conditions, then we think the convergence of a series makes sense, and we think Fourier series representation makes sense, and we'll make it a bit more mathematically precise. Okay. And okay, so let's first start with thinking about what does this convergence mean. Okay, or we give a little condition about what does the convergence mean in this course. Okay, so well, the thing we want to do is we want to have our series, so it's a sum from k from minus infinity to plus infinity of this ak e to the jk omega t. We want this to become our x of t. Okay, and as in standard calculus way, well, we think convergence as we are doing something finite and push the finite limit to infinity. Okay, so yeah, so summing over infinite terms are weird, but now we think about summing over finite terms. Okay, so if we sum k instead of minus infinity to plus infinity, and so we sum k from some minus big N to plus big N, so this is some big range of k, and we summing over all those harmonic related complex exponentials. So this is like the series truncated at some finite big N. Okay. And we define this as x of big N of t. So this is an approximation of our x of t, and we hope that this thing as n goes to infinity become our x of t. And we are going to see, we want to, so to study the convergence of this thing going to x of t, we want to study the difference. Okay, so let's just denote the difference. And so we define this approximation error term, E sub n. That is just our true signal x of t minus this x n of t, which is the finite summation of complex exponentials. Okay. So here are just definitions. And yeah, so we plug a definition as x of t minus this series summing over to k from minus n to big N. And what we hope is as n goes to infinity, this thing goes to 0. Okay. And okay, so if this thing goes to 0, then we are pretty happy. But there are many tricky points about what does it mean by En of t to go to 0. And actually, the thing we care about is not really En of t goes to 0. So we, in this course, we define convergence with this weaker sense that we want, instead of just En of t go to 0 for every t, for example, we just care about this energy of our error term. Okay? So we only want to consider this big E sub n. That is, you are calculating the energy of your error term. So you are squaring En and integrating over one period. Remember, in chapter 1, this is how we define energy. We say signal, we usually think signal is either voltage or current. So when you square N and integrating over one interval, that's proportional to energy. Okay. So this is the thing we actually care about in this class. Okay. And then, so the motivation of this is a good thing is that or justification is that you can check that if you want to make this thing as small as possible, then you need to pick AK such that AK equal to this expression, which is exactly the analysis equation. So we think that, so this is just a justification such to tell you that picking this En as our measure of error is pretty good, because that means our Fourier coefficient choice is pretty good. And the proof is kind of long, so it's 3 pages here, and we won't go into detail. And you can read the you can read the slide later. I should correct all the errors, so it should be correct. Anyway, so that's a 3 page. And anyway, so the idea of the convergence here is that as an increase, and so you are adding more and more terms. So the difference between x of t and this series hopefully gets smaller and smaller, because you are missing all less and less terms. Okay. So yeah. So as an increase, you hope that less terms are because you are like removing terms from En, and so you hope En decrease. Okay. And we just basically take this as a definition, saying that we say x of t has a Fourier series representation if only if En goes to 0 as n goes to infinity. Okay? So this is what we mean by having a convergence of Fourier series representation. Means that our En goes to 0 as n goes to infinity. Okay? So this is the smallest sense of convergence. But I'm still missing. Okay. Okay. And okay, so we want this kind of thing. And here is a proof of our AK actually minimize En, and we will skip it then. And okay, so those convergence, but convergence are sometimes not achieved. So here we give 2 examples of we won't get convergence. Oh, I see why I'm feeling weird. So I should get just me. Just a second. Presenter view. Oh. Okay, that is that. Let me fix this a little bit. Hopefully everything is fine. Okay. Wait. No, it's weird. Oh. PowerPoint is stuck. Excuse me. I think I crashed PowerPoint. Oh, okay. It's back. Okay. Yeah. So back to our convergence or not convergence. Okay. So we have 2 examples of things that are not converging. So first is that, well, we are calculating our AK from this analysis equation, and sometimes you just don't get AK from here because you are integrating something, and this integral can just diverge. Then if you diverge, you don't have AK. And you don't have AK, you cannot even write down a series. Then obviously you don't have a Fourier series expression, right? So that's a bad case. And another bad case is that even if you have AK, and then this summation of a series might not converge. So remember, we have this summation, we want K from minus infinity to plus infinity. And so we are summing over more and more terms. And well, if the tailing terms are not getting smaller, or maybe they just not getting smaller fast enough, so the summing over infinite terms can just blow up, etc. Okay? And yeah, so there are many ways that this thing can be non-converged. And here we are doing like positive listing. Okay, although there are bad things might happen, we will give conditions that such that if the signal satisfies this condition, then we know our system, our Fourier series will converge. For example, so the proof of those are pretty technical, and this is not a too mathematical course. So in this section, we will skip all the proof and we'll just state the result. Okay, so the first result here is that if our signal is continuous, this x of t is continuous, then we'll have En go to 0 as n go to infinity. Okay, and we'll also give two more set of conditions that have En go to 0. And in case of Dirichlet conditions, it has even higher, even better convergence property, as we'll see. Okay, and anyway, so let's see the first thing. The first property, or maybe a second property. So the first convergence property is if the signal is just continuous. And the second one is this finite energy. And if the signal has finite energy, actually the continuous is a little weird, but oh, okay. Yeah, so if the signal is finite energy, and by finite energy, well, energy is this term, so once again, you take the absolute square of your signal and you're integrating over one period. Okay, it's finite energy over one period. And so if your signal satisfies this, then first we can check that AK is finite. Let's see how. Okay, is actually true. Okay, I think this is a little weird, but let's assume this is true. And anyway, so as we said without proof, is if the signal has finite energy, then the area in the energy in the approximation area, so this is En. Remember, En is the energy of this small e sub n, which is the difference between your x and your xn. And so this big E sub n should go to 0 as n go to infinity. Okay, and here we are just writing the same thing in equation once again. So just reminding what's your small e of n and big E of n. So small e of n is your x of t minus your finite truncation, and big E of n is the energy of your small e of n. Okay, and so here is something that we want to stress, is that we are choosing a very particular condition for convergence. So here we are just saying this big En of n goes to 0. And that's very different from what you might think about being convergence. So you might say converge means that your x over t and your this x sub n of t should become the same at every t when n go to infinity. Okay, that might be something you think about convergence, but that's not what we are getting here. We are just getting this difference. So energy of the difference is 0. So we might want this difference to be 0 at every t, etc. But that's not what we get. We're just saying the difference has no energy. Okay. But we argue that this is good for us because we are thinking about engineering, and in engineering applications, if two signals have no energy difference, then they are practically the same when you are using them in your actual physical system. Okay, so this is our justification of picking this no energy difference as our convergence condition. Okay, so this is finite energy signal, and although I think this is question mark. I will mark this. I will check it later. Question mark. Anyway. Okay, so let's go to the Dirichlet condition we keep talking about. So those are conditions that give you a little better convergence. Okay, although this is very tricky, as we will see at probably end of today. Okay, so if you have Dirichlet condition, not only you have equal to 0, you also have this condition. So, okay, but you need to be very careful that for every t, and as n goes to infinity, x of n of t will go to x of t. Okay, so this is kind of what you want. But so spoiler, you need to be very careful about the ordering of the quantifier. So if you remember from calculus, the ordering of the quantifier is very important. So we have for every t as n goes to infinity, this is true. But as n goes to infinity for every t, so if you switch the order of those two quantifiers, then that's not true. Okay, so that's very tricky. But anyway, this seems pretty good. For every t, if you choose n big enough, your xn of t will go to x of t. Okay. Well, except for some t, where x of t was discontinuous. So that's just something bad that you need to accept. Okay. And we use this to justify using Fourier series representation to all our signals in this course because they will basically all satisfy the Dirichlet conditions. We're going to see that signals that don't satisfy them are very pathological. You need to be very bad to violate those Dirichlet conditions. And okay, so the continuous part of the signal, your series will converge to your true signal, and the discontinuity, it does the logical thing it should do. So your Fourier series will converge to the average of the left limit and the right limit. Okay. Any questions so far about our claims about convergence? And yeah. So anyway, point here is our convergence means big En goes to 0. This big N go equal to this thing. Okay. Okay, so let's see the Dirichlet conditions. So the first one, is that your x over t must be absolutely integrable. Once again, you are integrating over one period. And remember, this is a little different from the finite energy condition we just talked about. Finite energy means there's a square here, but we don't have a square here. We just have the absolute value, and integrating over one period, we want this to be finite value. Okay? So this is the first Dirichlet condition. And this will actually guarantee AK are finite. Now this makes more sense to me. Anyway, so this guarantee AK will be finite because you can just check the derivation here. So you take the absolute value of AK, and you use the analysis relation, and it's an integral of those things, and you pick the absolute value, and you can push the absolute value inside the integral, and that way only get your thing bigger. Then you take absolute value, and the absolute value of those two things, and the absolute value of the complex exponential just 1. So you are left with your absolute value of your x over t. But we just say the absolute value of x over t is finite, then you divide by t is still finite, so your AK is finite, and this is true for every k because, yeah. Okay. So a simple derivation, and we see that if x over t is absolutely integrable, then all the AK will be finite. So that's something nice, because if AK is not finite, then you don't even have a even have a series expression. Okay, and we will give a counterexample of things that violate this. Okay, so we'll do this for all three conditions. We'll give an example of violating a condition to give you more idea about condition. And here is the example. So x over t equal to 1 over t. Okay? And it's repeating with a period of 1. Okay? So between 0 and 1 is 1 over t, and between 1 and 2 then it's repeating this thing. So it's 1 over, I believe, t minus 1, something like this. Okay. And so if you remember calculus, then 1 over t, you do integration, and it becomes log t. So you have a log blow up as t goes to 0. Okay? You do this integration to 0, you have log of 0 is infinity, so you have some infinity when you try to integrate this part. Okay? So this is something violating our absolutely integrable. But yeah, any question? Okay, if not, then let's see condition 2. So condition 2, it says that if you are in any finite interval of time, then your x of t should have bounded variation. So so that means the number of minimum and the maximum should be finite during every period. Okay? So what does this mean? Once again, it's easier to see a counterexample. Okay, so here is a counterexample of things that have infinitely many minimum and maximum. So once again, we are just cutting off between 0 and 1 and pasting it periodic for our interval. And between 0 and 1, we say x of t equal to sine 2 pi over t. That means as t goes to infinity, as t goes to 0, then this 2 pi over t goes to infinity, right? And yeah, but the sine is periodic, so the oscillation of this sine function will get faster and faster as your t goes to 0, and it will actually get an infinite number of maximum and minimum around this t equals 0. Okay. So this will violate condition 2, and while not violating condition 1. Because this thing is still absolutely integrable, because you take the absolute value, then you see the absolute value is all less than 1 because it's sine function. Take the absolute value of sine is less than 1. Then you integrate 1 between 0 and 1, that's less than 1. Okay? So this satisfies condition 1 but violate condition 2. Condition 2 means that you don't have crazy number of maximum and minimum. You just have finite value in one period. Question? No. Yeah. If there's no question, then let's see condition 3. Condition 3 is even more crazy. So condition 3 means that, once again, in finite interval, and basically means in one period, you only have a finite number of discontinuity. Okay? And your discontinuity must be finite. Okay? And okay, so yeah, once again we give example of violating condition 3, but is good on condition 1 and condition 2, and we don't give total expression, but I think it's pretty clear in this picture. So it's a step signal, and it will have a discontinuity at half distance, and where the discontinuity and where the drop amount is half the height, and then you go 1/4 the distance, and you drop 1/4 the height, and 1/8 the distance, 1/8 the height, etc. And you can see that as you go into this one period point, which you actually pick A instead of 1. But anyway, so as you go to this 8 here, and you see you can have infinite number of discontinuity here, because just by the Zeno argument, you can always cut in half and half and half. You can cut it in a smaller and a smaller amount, and yeah, so you have infinite number of discontinuity here. And once again, this will break your differential conditions. Okay? So yeah, so those are the three things you want to avoid. Let's go through once again. So you want to be absolutely integrable, and you want to be bounded variation. Then finally, you want to have finite number of discontinuity. Yeah. Okay. And I guess let's go back to our square wave. So this is the example and application of our dilation conditions. So we see our square wave function has so this is a small part of a square wave. So we have a square wave between minus t1 and t1. So let's see that we satisfy all three dilation conditions. So if we integrate this absolute value through one interval, then it's absolutely integrable because the height is less than 1. And so the integration is, actually you can just do the integration. The integration is 2t1 times 1. So it's absolutely integrable. And the number of maximum and the minimum. Okay, so that's a little weird because we have a straight line, but straight line counts as one maximum. Okay, so the number of maxima and the minima are 1 or 2. So you have 1 maxima and 2 minima or 1 minima anyway. So you have about 3 maxima and minima here, and it's a finite value. And finally, the number of discontinuity. So there are discontinuity here, but once again, in one period, there are only 2 discontinuity. So that's also satisfied. So we see that our square wave satisfies all 3 dilation conditions. So it should have a pretty good convergence. So let's see how the convergence goes. So we try to add up our Fourier series to become our square wave. So we have 1 here. So here n equal to 1. So plotting our xn. So this is from k to -1 to +1, and then k from -3 to +3. So okay. So we had n equal to 7 and n equal to 19. So we are seeing we are getting closer and closer to our square wave. And also in the discontinuity is doing what we expected. So the discontinuity, we should have our value being 1/2, right? Because it's 1 here and 0 here, so it's your average is 1/2. Okay, so things are going good except when we now have a very high n. So n equal to 79. And something unexpected happened. So you expect you go to square wave, but you see you have this weird jiggle here, okay? And this is not quite going away. And actually, even if you take n to infinity, you will always have this jiggling here. So this will stay finite size as n go to infinity, okay? So yeah, so now that seems troublesome because we want our xn of t to go to x of t for every t, right? And isn't this not satisfying what we expect? And the answer to this is the spoiler that we talked before, right? So we say we need to be very careful about the ordering of our limit. So we say for every t, so you fix t first for every t, and you take n go to infinity, your xn will go to x over t. And this will indeed be satisfied because those jiggling, this overshoot here, as you take n go to infinity, the width of them will go to 0. Okay? So so width becomes 0, and so for every t, you can always pick n enough such that this overshoot is to the side of u, and you converge to 0. But on the other hand, if you fix the n, then you can always find some t such that you have some overshoot. Okay, so if you fix n first, then you can always find a t that's close enough to this discontinuity, such that you have a finite difference between your x over and x over t. And the value here is, I think, anyway, the value will be bigger than this 5%. Okay, it's a finite value. Okay, and so this is called the Gibbs phenomenon. So if you are trying to approximate a discontinuous function with Fourier series, then you will get this Gibbs phenomenon, where you get a finite overshoot. So where you get a finite overshoot that always exists even when n goes to infinity. And okay, so here we see that the Lagrange's objection to Fourier is makes some sense because you will have this weird phenomena, but we just overlook them, and maybe let's say we have our engineering mind, and we think the overshoot has zero energy because they have the width going to zero. Then we think this approximation of Fourier series to the square wave should be fine. Okay. And yeah. And here, some conclusions about what we said. Okay, so we have discontinuity. So xn is at a discontinuity. So there's some summary about this Fourier series square wave function. So on a discontinuity, as we see, our Fourier series converge to the 1/2 of the average of left and right. So here left will be 1, right is 0, then you average 1/2. Okay, so that's good. And at a continuous point, as we say, you need to be very careful about the ordering of the limit. So if you set the t to some value first, so for any t, then you are guaranteed that as n goes to infinity, your x of n of t will equal to x of t. But if you change the ordering, then that's not true. If you fix n first, then you can always find t such that this is not satisfied. And that's the Gibbs phenomenon. So as n increase, this ripple overshoot here will get compressed, so the energy goes to 0 because the width of this overshoot area goes to 0, but the height will stay the same. Okay? So that's a bit funny, but that's what happens when you try to approximate the discontinuous function with your Fourier series, which are continuous functions. Okay. Any question? Okay. Not. Then here is a bit summary. So we have 3 conditions of the Fourier series. Okay, sorry. So we basically define this En goes to 0. So big En goes to 0 as our condition for convergence of Fourier series, because En is what we can physically feel about a signal. And we say if so we state without proof. So we say if x of t is continuous, then En should go to 0, and if this x has finite energy, and En should go to 0. And also, if you have directional condition, then En should also go to 0. And also, you have even stronger convergence where you have this for every fixed t, x of n go to x of t. Although you have the Gibbs phenomena. Okay. Any question? Don't have any proof. Okay. So then we have 10 minutes, and we can give a very quick overview of the properties, and we'll see the proof and the details in Friday. So yeah. So that's the convergence of Fourier series. So basically, you want to check your directional conditions are satisfied. But now, assume we are having good signals and we have Fourier series, then we see that we have this back and forth. So we are basically representing our x of t in 2 different representations. So we can think it's representing x of t by just writing down x of t, or we can just write down its Fourier series ak, the set of ak. And we have this synthesis equation and analysis equation that let you transform them back and forth. Okay, so that's very nice. And actually, this transformation back and forth, we can get some properties. Okay. So for example, linearity. So let's say you have some two functions that are periodic with same period big T, x of t and y of t. And x of t have some coefficients ak that's related to x of t, and y of t have some coefficient bk. Then then we can directly from this get Fourier series coefficient of some signal z that is a linear combination of x of t and y of t. So z of t equal to ax of t plus by of t. Then the ck, which is the Fourier coefficient of z of t, will be just the same linear combination on ak and bk. So ck will be big A ak plus big B bk. Yeah? So it's nice, and this is only actually two sides. So if z is a linear combination of x and y, then c will be linear combination of a and b. And also, if c is a linear combination of a and b, then you can go the other way back and get z is a linear combination of the same x and y. So this transformation is linear. So that's very nice. So let's say you want to you should want to get the AK for like a summation of different terms, then you can just do that for different terms separately and add them together, right? And for the derivation, you basically just plug in your two formula directly. So once again, we have our favorite synthesis equation and analysis equation. And actually, all the derivation in this section is just you plug in them directly. But linearity is particularly easy because you see everything here is very linear. So if you put a plus b here, then obviously summation is linear. So you can separate a plus b to summation a to summation b, etc. And here also the integration is linear. So instead of x here, you have x plus y here. Basically, you can separate into integration of x and integration of y. Okay. So that's linearity. And okay, 7 minutes. I think I can go through all of them without proof. So time shift. So if we shift our signal with some time, so once again we start with x. We x of t has the coefficients ak. And now we think about what if we have another signal as a time shift by x, so x of t minus t naught, and what would bk? And you can just do a direct calculation. So you do bk and equal to this integration x of t minus t naught and change your variable, then you get the bk equal to ak and times the natural phase vector e to the jk omega naught t naught. The t naught is here. Okay? And so this is time shift. And just another thing we do in chapter 1, so what if we do time reversal? So if you have if you instead of x of t have x of minus t, then you see that x of t, then you will get basically flipping the index of ak. Okay. So ak of x over t will be a of minus k. Okay. As you can see the derivation here, there's a changeable variable. Okay. And also time scaling. Time scaling is funny. Okay. So if you change x of t to x of at, then the ak actually don't change because when you do time scaling, what you actually change, you change your fundamental frequency. Okay? So you are going to change into a Fourier series with different fundamental frequency. So your omega naught will become a omega naught, okay? And your period will become t over big A, because if you have bigger than 1A, then it actually squeeze your signal. Remember in chapter 1? So you do this time scaling, this will squeeze your signal and then you get a smaller period. Yeah. So this is what happens on time scaling. And multiplication. Okay, so this is something very funny. And we'll see, this is actually very general. So you have x of t with coefficients ak and y of t with coefficient bk. And you want to see what's the coefficient of x of t times y of t. Then is h of k, which is actually a convolution between ak and bk. So we see this is L and b, a sub L, b sub k minus L with L summation from minus infinity to infinity. And you see that if you think this L is actually an index to some function, some discrete time function. So this is actually a discrete time convolution, right? And this is a general thing. So you have the Fourier transformation back and forth. Then you have a multiplication of two signals on the side, and you have the convolution of two signals on the other side. But for now, here you just see the equation. So what do we mean is, you think this a sub L as a of L. So some discrete time function. This is a of L convoluted with b of L, right? Or maybe I should use k there. And yeah, and the other side is true. So if you go the other side, so you think about some coefficients, some function with coefficients ak times bk. So you have multiplication on this side, and you actually have convolution on the other side. So if you have coefficient ak times bk, then that will correspond to signal that's convolution between x and y. So it's the x of tau times lt minus tau and d tau. But okay, but now this side is a little funny because those are periodic signals. So we say it's convolution, but it's different from our definition because the integration only over one period. Yeah. But you can get this. Okay, so that's funny. Okay, that's interesting. So multiplication go to convolution, convolution go to multiplication, and then we have conjugation. Conjugation, you basically, we've seen this kind of derivation before when we talk about real function. So, but actually, basically what happens is you do convolution on your signal, then your ak will become a star minus k. Yeah. And yeah, so the derivation is, once again, you plug in the formula. And with a single derivation, when x of t is real, in that case, we have this ak equal to a minus k star. Remember, we have this derivation. Yeah? We have derived this before. So we say x of t is real, and ak should equal to a minus k star, or a minus k should equal to a star. And finally, we have this Parseval relation. Sorry, we have one more. But we also have Parseval relation, and this is more physically motivated. It means we have conservation of energy. And here also, so proof is in one of the problem that we will probably put this in homework here. And anyway, so conservation of energy means that we think about energy in terms of x. So there's energy in one period, and it's actually, well, I guess it's called energy preservation is really weird. But anyway, so we can think about energy of x over t, or in one period, and that will be same as energy in the ak. So we think about ak as a discrete time signal. Then its energy throughout every k is absolute value of ak squared, and sum over every k. So the energy in this time domain will equal to this energy in this k domain. So that's interesting. And finally, we have this differential and the integration property, where we take a derivative of x, and your ak will get this extra factor of jk omega naught, and if you do a reverse, so you do integration of x, then you will get this extra 1 over jk omega naught ak. And this is a bit funny, and so you need to be careful about the integration limit. So here this is only true if we define the integration from minus infinity to t. And also you see that you have a 1 over k here. And that means that this is ill-defined if k equals 0, right? Because it's 1 over 0. So a0 needs to be 0. And that's because you are integrating over infinite period, right? So if a0 not 0, then the integration gives you infinity, and that's bad. And new a0, you need to do the integration to figure out. And yeah, so those are the properties. And we'll see them in a bit more detail on Friday. Okay, any question? Otherwise, that's today. Okay.
它其实它要表达的是
这样，
说
这样，最大值跟最小，
在一个它的周期 t 的一个区间里面，然后它的那种极大极小值
是有限个，
有限的。
所以这里其实是反例，这里说有无限个是什么意思？就是说，如果的 signal 是这个，
是说
这个是反例，这个是说，对，在这里有无限多个最大最小，因为它是 1 over t 嘛，对，就是它是 sin 的1 over t 嘛，然后1 over t 在 t 变成0的时候会到无限大，所以它这个震荡会越来越快这样。对，这个是反例。
然后这个它是什么意思？就是说为什么它是0.05是怎么样
？0.05就是你别的地方算出来数字，但是就是只告诉你说会有这件事情，就是说这个高度永远会大于0.05，它就是永远都会有这个超过一点点的 ripple 这样子，超过。
所以这不是就是根据不同的状况会改变的一个数字，是吗？还是？
当然是你方选不同就会改变嘛。但是我们现在说我们 fix 这个 square 方选，就是这个高度是1的话。那这个 overshoot 的部分会超过0.05这样。
然后这个计算，
那个计算我们就没有说，就是别的地方，我这里就没有讲怎么算出来。
OK，
只是说它就是对的这样。
然后，那这个 compress 的意思就是说，它会从类似这样压成这样，但是那个高度不变。
对。
好，谢谢。
可是我之前问你专题，
你说那个你说专题？
对，我有记性。
我有回礼拜三下午，礼拜三下午不行吗？还是？
对，我想。
那我们可以找时间，我们找时间。我看一下，我礼拜四不太想看，帮我们排。我想看今天礼拜2。
下礼拜也可以。
那我们排下礼拜好了。专题，你知道我专题是做量子的吗？
对。
OK。你是OK。
就先了解看看。
对，我想说你是修科学，你是有修课吗？还是？
我还没。
你是有修这堂课吗？还是来找我而已？
对，我有修这堂课。
OK。你是大2是不是 ？OK。
然后先了解看看。
好，那我们下礼拜的话，不然，好吧，那我就偷懒一点。那我们下个礼拜1的，我想想看，偷懒的话，好，应该可以吧？那下个礼拜1的1点半，如何？还是下1
点半？我礼拜1除了1点半以外，1点半。
不然我们就晚一点，不然我们4点半。
可以，4点半可以。
然后你的名字是
陈明君。
陈，好吧，我先打陈，也可以。好，蔡，那就下个礼拜1。
好，谢谢。
好。